Hello everybody, and welcome to example 3. We are still looking at page 116 in the workbook here, and this is going to be our first example of using the Taylor error formula that you see up here at the top of the page to estimate the error in using a Taylor polynomial to approximate a function. Okay, and before we dive into this, I want to mention that this refers to an exercise that you've hopefully tried on your own, exercise 2 on page 120. You actually built the Taylor series for the function f of x equals sine x, and we're going to use some of the calculations that you did there to kind of guide us through this problem that we're about to do. Okay, so in particular, you used the third, fifth, and the seventh Taylor polynomial to come up with some approximations of the number sine of 2. And what we're going to do in this example is to figure out what's the maximum possible error in those approximations. Okay, so let's remind ourselves of some of the assumptions that we made back in exercise 2 on page 120. They gave us value of a to be 0. The value of c in our case is 2. That's just our name for this number, the place where we're doing our approximation. And the series that you found, I'm going to just see if I can sneak this in here. This was the series for sine of x. Looked like that. Okay, we'll use those things that you already calculated and things we were given to kind of guide us through this problem. Okay, so let's maybe start by just filling in the part of this chart over here to the right that you kind of already filled in back in exercise 2 on page 120. So you actually calculated the numbers that are in this second column here. Those were the approximations that you got using the Taylor polynomials. So hopefully for n equals 3, you came up with a number that looked like 0.6667. Okay, and then for P5, 0.9333. And then for P7, 0.9079. I'm just taking the answers from exercise 2 on page 120 there. What's going to be new in this problem is this column. What is the maximum error in those approximations? Okay, well, that's going to be the error between the approximations and the actual value of sine of 2. And let's go ahead and use our calculator to see what it thinks the value of sine of 2 is. Okay, you can do this on your own with your calculator. Just make sure that you're in radians. If you take sine of 2, here's what I'm hoping you'll get. 0.909297, and so on. Okay, so let's see if we can calculate those maximum errors that we're talking about. Okay, well, that's going to be going back and using this error formula up here at the top of the page. All right, so I'm going to leave a little space for us. And we'll start by seeing if we can calculate the error in this approximation 0.6667 for n equals 3. This is going to be the first of 3 error approximations that we do. Okay, so to figure out how much error there is in that estimate, we need to go up and use this formula at the top of the page for en. And remember how we talked about the tricky part of getting the error is figuring out what this number m is. It's the maximum value of the n plus first derivative. In our case, n is 3, so that means this n plus first derivative that we're looking at here is going to be the fourth derivative of our function. Okay, well, we have to calculate the fourth derivative. So our function was f of x equals sine of x. We need to take 4 derivatives of that, and we can either do this together by hand, or you can maybe look back at exercise 2 on page 120 and see what you got for the fourth derivative. This isn't too difficult, so I think we can maybe just sneak this in here. Okay, and finally we come to the fourth derivative. Derivative of negative cosine is positive sine, and there it is. Okay, so the absolute value of the fourth derivative is the absolute value of sine of x. And what we are interested in is what is the absolute biggest that that function could get. That's this number m that we're talking about. And in particular, we want to know what's the biggest that it could get on the interval from a to c, which in our case would be 0 to 2. Okay, well, think about this for a minute. What does the graph of the sine function look like? The sine function is just a wave, and what are its maximum and minimum values? Okay, if you were to graph this on your calculator, maybe you remember this from trig, the biggest and the smallest that it can ever get are 1 and -1. And so the absolute value of sine of x always has to be less than or equal to 1. Can't get bigger than 1. And so what we've just found is the value of m. Okay, and so to calculate our error, the rest of it is just to go back up to this formula. We just figured out the m, and to fill in the other pieces, the c, the a, and the n. Okay, so the error when n is equal to 3 is going to look like m times c minus a to the n plus 1 over n plus 1 factorial, and now we're just going to fill in the pieces. So up above we got m equals 1. We know that c and a are 2 and 0. And n is equal to 3, so those n plus 1s are going to turn into 4s. So we have to calculate 1 times 2 minus 0 to the 4 over 4 factorial. You can do that calculation, and what you're going to get is 0.6667. There is our maximum error that we've just calculated. Okay, so that's going to go in our table right here. And so what we're saying then is that this estimate that we found, this 0.6667, the maximum difference between that estimate and the exact value of sine of 2 is 0.6667. Okay. And now we're just going to see if we can repeat that process for n equals 5. All right, so the steps that we go through here are going to look similar. So this time the n plus first derivative would be the sixth derivative, always 1 power higher than our value of n. And if you continue these calculations up here, the sixth derivative is going to get us to negative sine of x. I'll let you confirm that. And then we're going to ask the same question, what is the biggest value that that could have? Okay, well, the absolute value of negative sine of x, that's just the absolute value of sine of x, so our maximum value is still 1. That hasn't changed. And so when we calculate the error for n equals 5, okay, we're going to just fill in the pieces again. M is 1 in this case. Okay, and then c minus a to the n plus 1 would be c minus a to the 6th over 6 factorial. Fill in the c and the a. Okay, they're still 2 and 0. That part hasn't changed. Okay, and this time we're going to get a maximum error that looks like 2 to the 6th over 6 factorial. You can punch that into your calculator, and what will come out is 0.0889. There's the maximum error with n equals 5. So let's scroll up to our table and fill that number in. Notice that that number is smaller, and it should be, because if we use n equals 5, this approximation of 0.9333 should be closer to the exact value, and the error indicates that it is. Now the maximum error is 0.0889, smaller than what we had at the first step. Okay, and finally, we just need to do that one more time for n equals 7. We're hoping we'll get an even smaller error this time. Okay, so if n is 7, we need to look at the 8th derivative of our function. And I'll let you confirm that if you take 2 more derivatives, you're going to get back to sine of x. Its maximum value is going to be 1 again. M turns out to not change in our problem. And then when we calculate the error, it's going to be the error for n equals 7 in this case. Okay, so we just calculated our m to be 1, and the c minus a this time is going to be raised to the n plus first power, which is 8. Okay, fill in the c and the a. Okay, and then our calculator can tell us that this time we're going to get a maximum possible error of 0.00635. Okay, fill that into our table up above. Okay, so let's scroll up. And notice that that's even smaller. Okay, and this is a good sign. We would like these errors to be getting smaller. That's telling us that these approximations over here in the second column are getting more and more accurate. So you can kind of see the behavior that we're getting here. What we're hoping is for our errors to get smaller and smaller as n gets larger and larger.